Good evening, everyone. This is the Polymer Reaction Engineering Live Session and Sample Problem Discussion, session number 9. My name is Rohan Jadhav, and I'm the TA responsible for live session and problem discussion. So, for this session, we'll be discussing about heterogeneous polymerization and its characteristics, such as there are different types of heterogeneous polymerization methods, such as bead polymerization and powdered suspension polymerization and bead suspension polymerization. So we'll be basically focusing on that. And heterogeneous polymerization, as you can tell from the name itself, it depends on the difference of the phase during the polymerization reaction. So we'll be discussing some sample problems, which will be useful for you to understand the lectures uh, which are which are published for this week. So starting from the first question, this is a problem that is if a person wants to prepare high impact polystyrene and acrylonitrile butadiene styrene copolymer using a combined bulk bead suspension polymerization, the water and dispersant should be added. Uh, then there is a dash, the phase inversion of the monomer solution. The step of the water and dispersant addition is required to dash, and you have to fill in the blank. So the first option is after the phase inversion of monomer solution. So we know that during polymerization of styrene and acrylonitrile, when it's initiated, it's under continuous stirring, and it is under continuous stirring until the phase separation or phase inversion occurs. So when the phase inversion occurs, only after that, in the final stage, water and dispersant are added to the system, and the polymerization is completed inside the suspension. So for the first dash, the correct answer would be that after the phase inversion of the monomer solution, which would then the step of water and dispersants addition is required to suspend the polymerized beads. Uh, as the polymerization is completed in suspension, so the polymerized beads formed should be suspended, and that's why this step of water and dispersant addition is performed at the final stage where the polymerized beads are suspended. Moving on to the next question. We have in semi-continuous and continuous emulsion polymerization processes, sufficient free emulsifier is usually required to. So we have four options here: to nucleate new particle crop, to stabilize the oligoradicals that precipitate in the aqueous phase, to saturate the surface of the existing interfaces and form micelles, or to increase the presence of available free monomers, resulting in regulation of the polymer characteristics. So what happens in homogeneous nucleation process is that there should be sufficient free emulsifiers available to stabilize the oligoradicals that precipitate in the aqueous phase. So in homogeneous nucleation process, what happens is that whenever sufficient free emulsifiers are present, oligoradicals will precipitate in aqueous phase. And in continuous emulsion process, during the heterogeneous nucleation, uh, during the heterogeneous nucleation process, what happens is there should be sufficient pre-emulsifiers to saturate the surface of the existing interfaces, particles or monomer droplets, and form micelles. So as you can see, that saturation of the surface of existing interfaces to form micelles will be is what correlates with the heterogeneous nucleation process, and the stabilization of oligoradicals that precipitate in aqueous phase also resonates with the semi-continuous and continuous emulsion polymerization processes. So, stabilization of oligoradicals and saturation of existing surface to form micelles. This is the correct option for requirement of sufficient free emulsifiers in the semi-continuous and continuous emulsion polymerization processes. Moving on to the next one, we have choose the correct characteristics of bead suspension polymerization from the following options. We have first, in bead polymerization, the polymer is soluble in its own monomer, Then in bead polymerization, the polymer is insoluble in its monomer. Resultant bead will be porous and irregular, and the resultant bead will be non-porous and smooth. So this question is from the basic definition of bead suspension polymerization and how the polymerization process occurs. So the bead formed from the suspension polymerization, the polymer bead is basically soluble in its monomer solution. So the first question, first option is the right one. Then in next one, the monomer polymer mixture is basically homogeneous. So the resultant bead which is formed is always porous and smooth. So it will be porous and smooth. Moving on to the next question, we have in vinyl chloride monomer VCM suspension polymerization process, overhead reflux condenser. Overhead reflux condenser. Example, this is your suspension polymerization tank. Just say that. Just say that. And we have a overhead reflex condenser, which is sending its reflex back to the polymerization chamber, suspension polymerization chamber. So, for the effective heat removal of the polymerization process, by increasing the reflux rate, the porosity and particle size density of the polymer should, and the next is non-condensable gases can get trapped in the condenser due to reflux. The trapped gases can dash. So, from the given options, we have increase uh, increase in particle size density or porosity, decrease in particle size density or porosity, reduce the heat removal efficiency, and interact with the polymers and affect its morphology. So, looking at this process from a standard chemical engineering point of view, we have overhead reflex condenser, which is used for effective heat removal of the polymerization process. Since the reflex is condensing, it is losing its heat. It is losing its heat, and it is being the cooled reflex is being again circulated back inside the chamber. So basically, we are removing the heat. By increasing the reflex rate, the porosity and particle size density of the polymer should, the correct answer would be increase, because since the overhead reflux condenser will have pure solution, this pure solution is again being supplied back to the suspension polymerization chamber, where uh, by increasing the reflux rate, the porosity and the particle size density (PSD) of the polymer will be increasing. And then next we have non-condensable gases can get trapped in the condenser due to reflux. So during this reflux process, if there is any non-condensable gas which is forming due to the reaction, or if there are non-condensable gases present in the reaction, they can get trapped inside this condenser. Since they are non-condensable, they won't condense and they will retain their heat. So because of that, the trapped gases can reduce the heat removal efficiency. Since they are retaining the heat, the removal of heat won't occur, and because of that, the polymerization process's effective heat removal will be hindered. Moving on to the next question. When relative velocity is similar to that needed to make a drop slightly unstable, a uh, number of tiny droplets are separated from the original one. This drop this drop breakage condition is referred to as thorough breakage, erosive breakage, and liquid film prevented coalescence and immediate coalescence. So, during this is related to the particle size distribution during heterogeneous polymerization process. So, the relative velocity when it is similar to that needed to make a drop slightly unstable. Uh, so, a number of tiny droplets are separated from the original one. So, if we look at the individual mechanisms, when we take a look at the thorough breakage, what happens during a thorough breakage is that a single droplet will be there, and it will undergo breakage very quickly, and it will be separating cleanly as two separate droplets. So a single droplet is pulled apart and completely properly separates into two droplets. That is for thorough breakage. So in the next uh, breakage condition, we have erosive breakage. In erosive breakage, what happens is the tiny droplet, it starts eroding. It will first deform into a non-spherical shape. The droplet will first deform into non-spherical shape, and what happens is the droplet will start losing its mass at the corners of the uh, non-spherical parts of the drop. So as you can see, first the drop exists, and then it starts deforming into non-spherical droplet, and then the areas where the non-sphericity is high, at that point the small drops start eroding away from the main body, and that's why it's called erosive breakage. So when the relative velocity is similar to that needed to make a drop slightly unstable, so the relative velocity which makes the droplet slightly unstable, which means that it is deforming it a bit, making it non-spherical, then the number of tiny droplets formed will be through the erosive breakage mechanism. So erosive breakage mechanism is the correct answer. What happens in liquid film prevented coalescence is that when there are two droplets, uh, since this is a coalescence process, the breakage condition is not applied on these. This is a coalescence process. So when there are two droplets together and there is a small liquid film in between them, what happens is that this liquid film, it prevents these two droplets from coming together. So these droplets cannot combine together, and that's why it is called liquid film prevented coalescence. And immediate coalescence is what happens when two droplets immediately combine, form a single large droplet. It is the exact opposite of, let's say, thorough breakage. Exact opposite. So the correct answer for this question would be erosive breakage. Moving on to the next question we have. For population balance modeling and suspension polymerization, consider a case where two drops are colliding and a continuous phase liquid fluid is stuck between the two drops. So just reading from this definition, you can relate it to the previous question where we just saw liquid film prevented coalescence. So if there is a small film in the middle uh, where two drops are colliding and a continuous phase liquid film is stuck between the two drops, which is stopping them from coalescing. So we have one drop, two drop, and then we have a liquid film which is preventing the coalescence of the two drops. Since the liquid film is preventing the coalescence of the two drops, for draining the liquid film, the dash energy of the trigger droplet oscillation must be greater than that of dash between the drops. The drop link is interrupted until the liquid is fully drained. So what happens is that for these drops to combine together, uh, the first, the first, mm, this usually occurs in turbulent flow, and two mechanisms have been postulated in literature for drop coalescence. First one is that the initial collision of two drops, a continuous phase liquid film is stuck between the two drops, which stops them from coalescence. And in second one, what happens is that uh, and because why this happens is that attractive forces, the draining of the liquid film can lead to drop coalescence. So what happens is that the draining of the liquid film, this liquid film needs to be drained so that these two drops can come together closer. So for that to happen, the energy of the trigger drop collision must be greater, which means that these two drops should be colliding with each other with a greater kinetic energy. Since potential energy does not have a role to play here, because only after the collision, uh, only after a higher kinetic energy collision would help in draining the liquid film on either side. The liquid film will get drained on both sides, and because of which, what would happen is that these two drops will come together, and that the trigger drop oscillation must be greater than the energy of the adhesion between the drops. So if adhesive forces are adhesive forces must be lower than the kinetic energy of the drop oscillation, liquid film drop oscillation. So because of that, what happens is since the what would happen if adhesive forces are high, that they would slowly just come together and liquid film won't be drained properly. But if the oscillation of the drops is higher, they will slowly oscillate the kinetic energy of the triggered drop oscillation will be high enough to slowly displace the liquid film between them. So because of that, kinetic energy of the trigger drop oscillation must be greater than that of the addition forces between the drops. Next question we have statement one. There are two statements you have to find out which is true and false. An increase of dispersed phase viscosity results in reduction of both breakage and coalescence rates. If we increase statement two, if we increase the input power per unit mass, increase in agitation speed in suspension polymerization, the drop coalescence rate will increase. So from a straightforward point of view, we can see that increase of the dispersed phase viscosity, eta D, results in reduction of both breakage and coalescence rate. Since the dispersed phase viscosity increases inside the dispersion medium, uh, since the viscosity is increasing, the the drops the drops breakage rates will reduce since the viscosity is high enough. They won't come close. Yeah, they won't be going far away enough so that the breakage will be prevented, and coalescence rate will also decrease because if there are two bodies, if there are like, for example, if there is a droplet like this in with a high dispersed phase viscosity, what happens is that because of high viscosity, as it deforms further, the breakage will stop. The breakage will be prevented. But if you have two molecules like this with very high dispersed phase viscosity, what would happen is that this high viscosity will also prevent the coalescence rate. Since the viscosity is high enough, they won't be moving towards each other that effectively. And because of that, both breakage and coalescence rates are hindered as dispersed phase viscosity is high. So first statement is true. So next one we have, if we increase the input power per unit mass, increase in agitation speed and suspension polymerization, the drop coalescence rate will increase. So in suspension polymerization, if you are rotating the suspension which is forming fast enough, the drop coalescence rate will increase. Why would this happen? Is that when you have droplets which are being rotated at a high velocity, you're basically forcing the drops to come together. You're reducing the you're reducing any kind of space between them since the agitation speed is high enough, and then the input power per unit mass which you're providing is also very high. So because of that, the droplets will come together, because of which the agitation process will provide higher coalescence rate, which will increase the coalescence rate of the suspension polymerization process. Next question we have. In suspension polymerization, the increase of hold-up fraction of the dispersed phase decreases the turbulent intensity. So, uh, in suspension polymerization process, what happens is that the increase of uh, hold-up fraction of the hold-up fraction of the dispersed phase is in the turbulent, it affects its turbulent intensity. Since the hold-up fraction is increasing, the dispersed phase is increasing. Psi, which is described as the turbulent intensity, will decrease because increase of the dispersed phase viscosity iteratively results in reduction of both breakage and coalescence rates, as we saw in the previous question. This comes under the effects of viscosity of continuous and dispersed phases on particle size distribution. So basically, if the holdup of the liquid fraction of the dispersed phase would decrease, increasing the holdup fraction of the dispersed phase will result in decrement of the turbulent intensity in suspension polymerization process. What is the characteristic? What is the characteristics that affects the weatherability and resistance to hydrolysis of emulsion polymer, copolymer, emulsion polymer or copolymer? So we have four options here: copolymer composition, molecular weight distribution, and gel content. So gel content comes under polymer architecture, which describes its different properties, and same goes for rheology. So molecular weight distribution has some role to play in the characteristics which describe the variability and resistance to hydrolysis. But the copolymer composition has direct effect on the resistance to hydrolysis, and it also affects the glass transition temperature of the polymer. So because of that, uh, it affects the weatherability and the affinity to hydrolysis. It has a greater role in determining the weatherability and resistance to hydrolysis of the emulsion polymers. So correct answer would be the com copolymer composition. Next question we have, what is the characteristic that affects the shear and peel resistance to hydrolysis of emulsion and copolymers? So previously we saw the weatherability and hydrolysis properties, which was dependent on copolymer composition. Now we are seeing shear and peel resistance of hydrolysis emulsion. So for peel resistance is determined by intermediate molecular weights, which is usually seen for adhesives, since peeling of adhesives, uh, if you're easily able to peel off an adhesive, it's not good enough, right? So that's why intermediate molecular weight adhesives are used for